Today's topic is the binary adder, that is the half adder and full adder. The topic code is ELEC-DIGIE-S7. Now, a binary adder, to form a binary adder. Now we would like to make binary adders and subtractors and so on. To make a binary adder, as we have discussed all the addition process, the binary addition, multiplication, division, etc. Now we are in a position to define a binary adder. Now, binary adders are arithmetic circuits in the form of half adders and full adders to be used to add together two binary digits. Okay, so the binary adders are arithmetic circuits which are used to add together two binary digits. Now, another common and very helpful and useful combination logic circuit which can be constructed using just a few basic logic gates, allowing it to add together two or more binary numbers, is the binary adder. A basic binary adder circuit can be made from standard and exclusive OR gates, allowing us to add together two single bit binary numbers A and B. The addition of these two digits produces an output called the sum of the addition and a second output called the carry or the carry out, carry out bit according to the rules for the binary addition. One of the main uses of the binary adder is in arithmetic and counting circuits. Consider a simple addition of two numbers to the base 10. Ternary with decimal base 10 numbers as given below. Now let's say that we have, this is a one number 123 and 789 is another number. We would like to add them in decimal numbers as human do. The addition, these two numbers we would like to add. Now this is a number A and this is a one particular total number A which is comprising of the three digits. Okay, and this is comprising of also the three digits. So these two digits, first digit 3 and 9, so this is A1, this is A2, A3, this is B1, B2, B3. So it will have collectively we can call it A, number A, and this is B, but we have to add these individual these three digits each numbers together. The first digit of this A and the first digit of the B, first digit of the A, second digit of the A and second digit of the B, third digit of the A and third digit of the B. So what we call the number which we are adding is called augend, and the number is going to be added is called addend, and the result is the sum. Okay, so in this case when we add these two we get 912. Okay, so we add 9 plus 3 is 12, 1 is carried, so 8 plus 10 is 8 plus 2 is 10, 10 plus 1 is 11, and so on and so forth. 1 is carried here, 7 plus 1 is 8, 8 plus 1 9, so 912 is the answer. This is the decimal number system. From our math lesson at school and various learning places, we learned that each number column is added together starting from the right hand side, and that each digit has a weighted value depending upon its position within the column. When each column is added together, a carry is generated if the result is greater than or equal to 10. Okay, so in the base the base number, which base number in this case is 10, or it could be any base number. This carry is then added to the result of the addition to the next column to the left, and so on. Simple school math addition. Add the numbers and carry. Now the adding of binary number is exactly the same idea as that of the adding together decimal number system numbers, but this time carry is only generated when the result is in any column is greater than or equal to 2. So the base number is the base number of the binary. In the other words, that 1 plus 1 creates a carry. 1 plus 1 will create a carry, because 1 is the largest number, in this case 0 is the smallest. So in the base 2 it will carry 1, it will generate 1 carry. So binary addition follows these same basic rules. Now let's go directly, you read it out, and this explanation is given how we add these two. So here what we have the rule, this is oggend, this is addend. Okay, 2 bits we are adding here. Whether you with a 1 plus 0 is 1, the sum is, here we have the 1, the carry is 0. 0 plus 1 is 1, sum is 1, the carry is 0. 0 plus 0 is, sum is 0, carry is 0. But 1 plus 1, the sum is 0 and carry is 1. Just like we have 9 plus 1. Okay, example like it, we can give that. So when we have 9 plus 1 in decimal number system, then the next number we don't have, we put the 0 and 1 is carried to the next column. So let's come to the directly a half adder. Now binary adder, this is a half adder. Binary adder, how we add these numbers. This is the block diagram. First building block of the binary adder is the half adder. Half adder consists of the inputs A and B, 2 inputs and 2 outputs. Inputs A and B, which gives rise the output sum and a carry out. Sum and a carry out. So if you add two numbers A and B, it will give you sum and a carry out. So remember, a half adder consists of 2 inputs and 2 outputs. So what it consists of inside, we would like to see inside which circuit constitutes this half adder. So we have, let me go to directly to the circuitry of that. We having a moment, yeah, here it is. This is a half adder circuit. So if you see that this is now a half adder, same half adder which has 2 input 2 outputs. So how internal circuit is arranged with the logic gates, we have exclusive OR gate which gives the sum, and AND gate which gives the carry. So here is the calculation. You can see when we have 2 bits addition, A and B. Let's say B has all the possible values, 0 0 1 1 0 1 0 1. Now let's see whether these will give rise the same result or not. So when A and B are fed into the exclusive OR gate, the output, when B is 0, A is 0, the sum is 0 and the carry is 0 in this case, because when you multiply these 0 into 0, the carry will get equal to 0. But if you recall and see, go back and see the exclusive OR gate, you will get also the sum is equal to 0. Now similarly, if B is 0, 1 is 0, B is 0, A is 1, the sum is 1 but the carry is 0, because 0 here you feed A into B, which is 0 into 1 is 0, so carry is 0. Similarly, 1 and B is 1, A is 0, the sum is 1 and the carry is 0. If you remember, we call it output is equal to 1 if inputs are unequal. It's inequality detector. Exclusive OR gate was also termed as inequality detector. So when both are in 1, the output is 0. So in this case, 1 into 1, the output is 0, but the carry is this time is 1. Here 1 into 1, A into B is 1, so carry is 1. So this is perfectly 2-bit binary adder. That is enough for 2 bits, only 2 bits, not more than that. Okay, so 2 bits for that work fine. So here is the sum relation A exclusive RB. This is the exclusive RB symbolic notation, and the carry is A and B in this case. Now coming to the full adder circuit, now we would like to have because the half adder does not have ability to add a carry bit, because here we have, if we have any carry bit, then it is not able to add that bit. So because we need, when 2 bits are added, then it may generate a carry, so it carry will go on. So that has to be a circuit which can deal this carry bit. So here is the full adder. Full adder has 3 inputs, 2 outputs, 3 inputs A and B, and a carry bit, carry in, whichever the next column, which like the half adder adds 2 bits. If a carry is forwarded, that will be taken by the full adder. So that's how the 3 inputs and 2 output, which is again the sum and a carry out. So this is very simple, the diagram, block diagram. Okay, but we will look into it what is inside, which constitute this full adder. So we have the now carry in here, A plus B. It will be adding these 3 numbers, now 3 inputs, carry in A and B. It will give a sum and a carry out. Now the full adder is a logical circuit that performs addition operation on 3 binary digits, just like the half adder. It also generates a carry out, the next addition column. So now let's see this is the inside the big full adder that constitutes the complete logic circuit. 2 inputs, okay, 1 C in carry in and 1 sum and the other carry out. Now what we have, it actually is made from the 2 half adders. One full adder is made from the 2 half adders. First half adder we feed the 2 AB, then what we have, A exclusive R B, we get output, then we carry is A into B. Now what we do here in this case, the circuitry, we take another second half adder, to which the output of the first adder, which is having the sum, is fed into the first input, and in the second input the carry bit, which is being generated by the first 2-bit half adders, whatever the numbers, is fed here. That is fed here into the second the half adder, while the carry bit of the carry bit from the first half adder is fed into the OR gate, and the output from the half adder, second half adder, the first output, which is the sum, is coming up exclusive A exclusive or B exclusive C in, because it is now making with the C in input here, carry input. These two will make, okay, this one and this one. So see here is C in, the carry in, and between these two, this is the first A exclusive RB coming, but this A exclusive RB is a one single unit is making another exclusive R with the C in, so that will constitute a sum. And similarly the second, the carry out, is actually the C in. Here we have got the, which is the carry in coming from here and into, which is A B, obviously this is a multiplication of these two input. So C input, carry in, and A exclusive RB, then these two are fed here, this one and obviously OR gate. So C in will be added further here, carry out, make it carry out. So that is the further detailed logic circuit diagram internally. This is the first half adder. If you see that, let me if you can let me make it into the blocks. So here we have, this is the first adder, this is the second adder. Here we have exclusive OR gate and AND gate. the output of this is the fed directly exclusive OR gate A exclusive RB to the input of the second adder, which is goes to the exclusive OR gate. Here we get the this is the two inputs what we are getting, and the C in goes to the second input of the second adder, while the carry bit goes to the directly to the OR gate, and another carry bit from here will give you the which is the A exclusive OR bit, A exclusive OR B into C in will go into it, which will be making NC out. So this is the exclusive the total truth table for both full adder. We can say that it's a full adder exactly. It will make the 3 digits. Since now 2 raised to power n is input is 3, 2 raised to power 3 means the 8 combinations of each the binary variable will be made. So as we have 4 zeros, 4 ones, again 2 0 2 ones, 2 0 2 ones, 0 1 0 1 0 1, and so on and so forth. This is now the output. You can we add simple mathematics. You can see this normally we have 3 bits are now added. 0 0 0 plus 0 plus 0 is 0. Sum is 0. C out carry is 0. Again we have now if A is 1, then the sum is 1, carry is 0. B is 1, sum is 1, carry is 0. Now if A and B is 1, the sum is 0, carry is 1. Now if we have the carry is 1 but A and B are 0, then again sum is 1, carry is 0. And similarly you can see the last one, when you come to here, all of the 3 bits when are 1, then we have sum is 1 and carry is 1 again in this case. So that's how it adds up the carry bit as well. Now here is the expression for it. Now this is sum is equal to A exclusive RB, A exclusive RB into OR gate. C input is equal to A exclusive RB again, which is exclusive or C input. Similarly for carry out bit, this is sum and a C in bits. For carry out bit is equal to A and B, or C in A exclusive or B. This is A exclusive or B complete that operation of the exclusive OR, and is equal to A and B plus the C in, that is we are the same. A and B is written here again, and C input A exclusive RB. So with this we reach to the end of the topic. See you next time, inshallah. Thank you.